Can we please welcome Kang, presenting on Breaking Composure, Journey to Hunting Windows COM Vulnerabilities. Thank you.
Okay, so hello everyone and welcome to my talk. And today I will be talking about Breaking COMposure, a journey to hunting Windows COM vulnerabilities. And this presentation focuses on what is COM component and how to find vulnerability in Windows COM component. And before starting the presentation, I will introduce myself. And my name is ByungHyun Kang, you can call me Kang. And I'm from South Korea, and I majored in computer science at South Korea. And my main interests are Windows bug hunting and system bug hunting, like anything. So, what can you expect from today's talk? Here's the agenda. We will start with the basics, what exactly are Windows COM components. After that, we will dive into what kinds of COM vulnerabilities have been found in the past. Then comes the main part of the talk. I will share my personal journey of finding a vulnerability. To wrap things up, I will talk about future research possibilities in this area. And then we can open it for questions. And first, Windows COM is a core component of the operating system designed by Microsoft to enable seamless communication between different software components. Acting like a universal translator, COM allows for interoperability between programs written in different languages, such as C++, C#, and Python. This capability is why many Windows functions, including embedding an Excel file into a Word document or communicating with a printer driver, are built on the COM. In a sense, COM serves as the key technology that connects various applications and operating system components within the Windows environment, allowing disparate software to work together as a cohesive whole. Now that we understand why COM is and why it's so important, let's talk about how its components are actually structured and how they run. This is a crucial distinction that affects how developers build and use COM objects. Essentially, COM components fall into two main categories. First one is the in-process component model, and second one is out-of-process component model. Let's break down what each of these means and why the difference matters. First, in-process COM is a high-performance model where the client and COM server run within the same process, sharing the same memory space and communicating through direct function calls. While this direct communication offers minimal performance overhead, it poses a security risk because the COM server inherits the client's privileges and operating with the same level of access as the user. This means any code executed in the COM component runs with the authenticated user's permissions and making this model unsuitable for our security research. And second one is out-of-process COM. Specifically, the local server's models operates by running the COM server as a separate standalone process like .exe files from the client application. This architecture enhances system stability as a server crash does not affect to the client. From a security standpoint, this separation is where the primary risk lies. The COM server often runs with elevated privileges such as system, even if the client application is running with standard user privileges. This privilege disparity makes out-of-process COM a critical area for security research. An attacker can exploit vulnerabilities in the highly privileged COM server from a low-privileged client. If successful, this can lead to privilege escalation, where the attacker gains control of the server process and, by extension, its high-level permissions. This type of attack is a classic and valuable vector for malicious actors, and making this COM model a key target for security researchers. And next one is the remote server COM model, also known as DCOM. Extends the out-of-process architecture by allowing a client and server to communicate over a network, typically use TCP/IP. This enables a client with low privileges to interact with a highly privileged COM server on a different machine. Similar to the local server model, but the primary security concern is privilege escalation. An attacker can send malicious data over the network to exploit vulnerabilities in the remote server. This network-based attack vector is significant because it allows a low-privileged user to gain high-level permission on a remote machine, making DCOM a historical critical target for remote code execution and privilege escalation attacks. Indeed, a critical similarity exists between the local server and remote server. Both rely on cross-process communication, where a low-privileged client sends data to a separate, often highly privileged server process. This shared architecture, which uses proxies and stubs to measure data across a trust boundary, creates a prime opportunity for security exploitation. The server running with elevated permissions must robustly handle all incoming data. If it fails to properly process malformed or uninspected data from the less trusted client, a vulnerability can lead to a crash or, more critically, like arbitrary code execution. This makes both model attractive target for privilege escalation on a local machine and remote code execution across the network, as the core attack vector is the same, exploiting data handling across the trust boundary. So does this mean we can simply send malicious data to a remote COM server and get it to crash? Well, the short answer is no. It's not that easy. Microsoft has built security validation into the COM object model to prevent that very thing from happening. So what kind of security validations are we talking about? Let's find out. And first tab is launch permissions, or a core COM security feature that controls who can create an instance of a COM object. Before a client can even get a reference to an object, the COM runtime checks these permissions. If the client doesn't have the necessary rights to creation fails. This acts as a crucial first line of defense, completely blocking unauthorized clients from interacting with the object's interfaces and preventing potential attacks from ever starting. It's great to see how the two-tiered security model works. Think of it as a two-step process. You need to get through both gates to interact with the COM object. The first gate is launch permissions, which is the initial check that determines if a user is allowed to even start the COM server process. The client's co-create instance call is validated, and if the user has the right to launch the service, the process begins, but even after this, they haven't gained control. That's where the second gate, access permission, comes in. This check determines whether the client is allowed to actually call the object method and interact with its interface. This two-part system is a powerful defense mechanism, and as a user might have the permission to start a process but not to use its functions, effectively stopping an attack from a low-privileged user before it can exploit a highly privileged user. The COM security model is a two-part system that uses both launch permission and access permission to protect COM objects. The first layer, launch permission, determines whether a user can start the COM object process. If a user is granted launch privileges, the process begins. The second layer, access permissions, then controls who can actually interact with the learning object and call its functions. This dual-layer approach prevents a user from exploiting a privileged service, even if they can get it to learn, making it a crucial aspect to securing cross-process communication. Alright, we have covered the what of COM, and now let's get into the how. The central problem is how a COM client can call a method in a separate process or on a different machine. Since the operating system isolates process for security, the solution to this is found in the proxy and the stub. These two components act as a bridge and translator, facilitating cross-process communication. They perform a crucial function called marshalling, which is the process of packaging data and method calls so they can be sent from one process to another. This enables seamless interaction between the client and server despite their physical separation. The proxy and stubs are two essential components that enable communication. The proxy located within the client's process performs marshalling to package the method name and parameters for transfer when a client makes a call. This packaged data is then sent across the process boundary via a communication channel like RPC. Next one, the stub is located in the server's process, receives the data and performs a marshalling to reconstruct it into an unusable format before making the actual call to the server's method. When the server completes its task, the results are measured by the stubs and sent back through the proxy and finally returned to the client. This transparent system allows to seamless communication even though the client and server are separate. Standard marshalling is the default and most common method for data transfer between a proxy and stub. It's a key convenience for developers because it is automatically handled by the system for universally recognized interfaces like IUnknown and iDispatch. This means developers do not have to create their own proxy and stub components as their necessary code is provided by core Windows system libraries like OLESR2.dll. This built-in approach simplifies development, ensures consistency, and enhances security as the code has been rigorously tested. As a result, developers can focus on their application's logic rather than low-level communication protocols. Now let's move on to the second type of marshalling, custom marshalling. This method is used when a COM object utilizes non-standard interface, requiring the developer to define the entire communication process. This is done using an interface definition language file, which acts as a blueprint specifying how data should be packaged and unpacked for the proxy and stub. Developers use a MIDL compiler to automatically generate the proxy and stubs DLLs from the IDL file. While this method gives developers the flexibility to create unique COM objects, it is a prime target for security researchers because any errors in the custom defined IDL or the generate code can more hurt ground for security research compared to standard marshalling. Okay, let's talk about COM threading models. The single thread apartment model is a COM threading model designed for simplicity and stability. Its core rule is that a COM object can only be called by a single, dedicated thread. This means the object does not have to manage the complexities of multi-threading, such as race conditions or deadlocks. All calls from other threads are automatically serialized by the COM routine, and ensuring that only one call is processed at one time. This simplifies the development of the COM object as it can be written as if it only ever receives synchronous or single-thread calls. The multi-thread apartment model is a threading model designed to allow multiple threads to call a COM object simultaneously. In this model, the COM object itself is responsible for ensuring thread safety. Developers must use synchronization primitives like mutexes or semaphores to protect shared data from being accessed by multiple threads at once. This makes the MTA model a prime target for security researchers. If a developer fails to correctly implement thread-safe code, a race condition can occur where the outcome depends on the execution order of multiple threads. This can lead to data corruption or unexploitable crashes. Therefore, unlike the STA model where the COM runtime handles serialization, the MTA model places the burden of security of the developer's implementation, making it a key area for finding potential vulnerabilities. To recap what we have covered about COM, first, we learned about the three COM types: in-process COM, local, and remote. Second, we saw that Microsoft implemented security validation, including access and launch permissions. As a researchers need to check both permissions during their analysis. Third, we look at how Proxy and stubs enable a client to call a server's method indirectly. Finally, we covered how COM measures data either using standard marshalling for default interface via OLE32.dll or custom marshalling for non-standard interface based on an ideal file. Now that you know all these details about COM, you might be asking yourself, why should I care? Why is a COM good target for bug hunting? It's a fair question, especially with so many other areas to focus on in security. Well, the answer is simple, yet incredibly powerful. COM is a goldmine for privilege escalation in Microsoft Windows. COM is a critical attack vector because it provides a communication channel between a low-privileged client and high-privileged COM servers. An attacker or researcher can use a client running with a normal user to find and exploit vulnerability in a COM server. For instance, by leveraging a flow in data processing or logic, they can gain control of or a cache or high-privileged process, which is a direct path to privilege escalation on the Windows system. This same principle applies to sandbox escapes, where a client within a restricted sandbox can exploit a COM vulnerability to break out and gain a higher level of system access. The security landscape is constantly changing, and we are seeing a clear trend. Windows 0-day exploits are on the rise, and at the same time, they are getting tougher to find. The low-hanging fruit has largely been picked, and attackers and researchers alike are having to work harder to discover a path to a high-impact bug. So for those of us who are serious about vulnerability research, the big question remains, where do we look for the next generation of vulnerabilities? We need to find something that others might not be focused on. We need to look at the older, more foundational parts of the operating system that are still in use today. These areas are often overlooked, but they remain a key part of the attack surface. And this is exactly where COM comes in. By diving into the deep, often neglected world of COM, we can uncover new and powerful attack vectors that others have missed. And let's see the previous research of COM. A study presented at COM Race at Usenix in 2022 successfully detected race condition bugs by focusing on the MTA COM object model. This research is highly relevant as it found several vulnerabilities by targeting a bug class that is notoriously difficult to find. It serves as an excellent example of how a focused methodology can yield significant research and provided the groundwork for my own research. Let's look at one more relevant research paper, also from Usenix 2023. One is titled Detecting Union Type Confusion. While the previous paper focused on the race conditions, this one is all about a completely different type of type confusion. The researchers discovered that if developers improperly use a fundamental C++ concept like union types or the variant struct in their COM objects, it can create a vulnerability. This is very interesting find because it shows a completely different way that COM can be exploited. Instead of focusing on concurrency issues, this research highlights how a simple mistake in data handling can lead to a serious security flaw. This is a great example of how even basic programming errors can have huge security implications in a complex system like COM. Now let's check out the real-world example of COM bugs to see how these concepts play out in practice. This first one is CVE 2020-1362, a bug that was discovered in the Windows Wallet service. For those who might not be familiar with it, this service is a core component of Windows that is responsible for handling user-sensitive payment and credit card information settings. The COM object found in the wallet service.dll library is not a standalone program. Instead, it runs with high privilege as an auto-process server hosted by svchost.exe. This setup allows a low-privilege client to interact with a high-privilege server, creating a dangerous scenario. A vulnerability was found in the wallet X-Factor interface, which provides a direct path for privilege escalation by exploiting a flaw in how it handles data. The vulnerability is located in setGroup function of the wallet custom property class. A logical flaw exists where setting the argument a4 to a value other than -1 bypasses security and validation checks. This bypass allows the attacker to achieve an arbitrary write primitive where they can control both of data and to be written and the memory address. This highly dangerous capability can be used to override critical data or hijack program execution and ultimately lead to privilege escalation or remote code executions. This vulnerability provides an attacker with a path to privilege escalation by allowing a low-privileged client process to crash a COM server running with system privileges. The core of the issue is a write what where primitive, which gives an attacker the ability to write arbitrary data to any memory location within the high-privileged process. While converting this primitive into a reliable exploit to achieve full code execution can be challenging. The ability to override critical data, modify function pointers, or inject malicious code makes this a critical and dangerous vulnerability for privilege escalation on Windows systems. Then there is a second bug we can examine, CV 2020-1404, found in the capability access server service. This is a classic example of a race condition bug. The capability access server itself is a Windows service that has various COM interfaces, and the vulnerability was discovered in the Windows UI start screen second tile interface. The capability access server service and its Windows UI start screen secondary tile interface are configured to use the MTA threading model. This is a crucial detail as it confirms that multiple threads are allowed to access this COM interface simultaneously. In the MTA model, as we have discussed, it's up to the developer to ensure thread safety. The COM runtime doesn't enforce a queue or serialized calls. Instead, it allows concurrent access to the object's method. This design choice, while excellent for performance, creates the perfect environment for a race condition bug. If the developer failed to use proper synchronization to protect shared data, multiple threads trying to access the data at the same time can cause a chaotic and unpredictable state. One thread might read a value just as another thread is in the middle of writing to it, leading to data corruption or a crash. This is precisely the type of bug that can occur in an MTA interface. And in the case of CV 2020-1404, it led to a serious security vulnerability in a core Windows service. And let's deep dive to capability access server. The start screen has various interfaces. Among those, a specific vulnerability was found in the I-secondary tile 2 interface. We can look at the IDL file for this interface and see that it has 12 different methods. Okay, let's get practical. How do we find their interface? We can use a decompiler to look at the COM server's binary file. When we load the DLL into a decompiler, we can navigate to the RData section. The RData section of a binary holds read-only initialized data. This is where you will often find crucial information about the COM interfaces, including their GUIDs and the vtable pointers. By examining this section, we can identify all the COM interface the service implements. The decompiler helps us trace these pointers and match them to the actual code that implements the method. The vulnerability starts in the put phonetic name method, which calls the save h string function. Since this happens in a multiple thread apartment environment, where multiple threads can access shared resource simultaneously, a race condition can occur. The analysis must focus on this pointer, which acts as a shared pointer in the multi-thread apartment model. In this environment, a race condition bug can easily occur when shared resources are used incorrectly. And the save h string calls the initialize function using this pointer. Within the initialize function, we find the critical area for a race condition, a call to free and assign on success. This is a major red flag for a bug hunter. The free and assign on success function is calling the Windows delete string API, which is a standard window function used to free memory allocated for a string. You might be thinking, but isn't this function supposed to just handle the free something? Yes, you're right. It's supposed to free a string that has already been created. The problem is what happens right after that. The code then calls free assign on success. This is the core issue. What's missing here? The code has no locking mechanism or any sort of value validation routine. There's nothing to ensure that another thread isn't trying to access or use the string after the first thread has already freed it. So what's happening? The race condition? Thread A calls freeze to release the string memory. Before the operation is complete, thread B tries to use the same thing, pointer. Because the memory is being deallocated, thread B's attempt to use it will lead to an access violation, a crash, and a potential denial of service. The worst case scenario is that an attacker can control the timing of these two threads to create a predictable crash, which could then be used as a stepping stone to a full-blown exploit. This lack of proper synchronization and validation in a multi-thread environment is the fundamental flaw that leads to a race condition. It's a classic example of a bug that wouldn't exist in a single thread model, but becomes a critical vulnerability in an empty COM object. The research findings demonstrate that COM is a highly effective attack vector. A significant number of the vulnerabilities discovered could be used for privilege escalation or escape sandbox to system-level privileges. This proves that COM is not just a theoretical attack surface, but a practically and valuable path to bypass sandboxes and achieve a full system compromise. The complexity of COM particularly is out-of-process and remote server models and their reliance on cross-process communication creates a rich hunting ground for security researchers, confirming that understanding this architecture nuance can lead to a full system compromise. Given the vast number of COM objects within the Windows ecosystem, the research we have discussed is a powerful starting point, not a conclusion. The findings from other researchers confirm that privileged out-of-process COM components, particularly those using custom marshalling, are a rich source of critical vulnerabilities. This provides a clear methodology for finding new bugs. The sheer size of the Windows operating system means that the attack surface remains too vast to be fully explored, confirming that COM is still a fertile and exciting area for security researcher. Now, how do we actually find these COM objects? Simply knowing they exist isn't enough. We need a way to enumerate and inspect them. The first step in any COM research is to use a tool that can show us everything that's out there on their system. One great tool for this OLreview.net, which was developed by security research James Forshaw. OLreview.net acts like a powerful explorer for all the COM objects on your computer. It reads information directly from the Windows registry, where COM objects are registered, and present it in a clear, organized interface. This allows you to see the class ID like CLS ID, interface ID, and other crucial details for every COM object. One of its most useful features is its filtering capability. You can easily filter the massive list of COM objects to focus on what you are specifically looking for. For example, you can filter by threading model or by server type. This allows you to quickly narrow down your search to privileged auto-process server likes, the very type of components we have identified as prime targets for privilege escalation bugs. It's an incredibly helpful tool to begin with, providing the essential map you need before you start digging into the code. To find a bug in a COM object, you have two main options, manual code auditing or fuzzing. While auditing can be effective for finding logical flaws, it's often too time-consuming. Fuzzing, an automated technique that feeds a program with random data to find vulnerabilities, is a more efficient alternative. To be effective, modern fuzzers are coverage guided, meaning they track which code paths are executed and then create new inputs to explore unreached areas. Getting this coverage information for a COM server, which often get coverage in runtime process, it can be difficult. This is the core challenge. How can we get reliable coverage data without the complexity of traditional method? There is an example of getting a coverage in runtime process by CyberArk, but isn't it there has the easy way? I see two main options for our COM object fuzzing approach. One is the KAFL, and next one is the What the Fuzz. KAFL is a powerful hardware-assisted fuzzer that uses inter-process trace for efficient, low-overhead code coverage. This makes it ideal for fuzzing complex privileged process like those in svchost.net, where its hardware-level visibility is a significant advantage. And What the Fuzz, on the other hand, is a more versatile general-purpose fuzzer that uses software-based instrumentation. It's easier to set up and is a great choice for a wider range of users and corner mode targets on both Windows and Linux without requiring specific hardware features. Let me introduce Greater for this KAFL. It's a fast guided fuzzer that's built for virtual machine, which makes it perfect for anything running as QEMU or KVM guest. This is a crucial advantage when fuzzing privileged Windows services, as it allows us to isolate the target in a controlled environment. So what makes KAFL so useful for us? It gets code coverage by counting instruction hits at a target address inside the Windows VM. This is a very efficient and low overhead way to monitor execution. Instead of relying on slow software instrumentation, KAFL leverages hardware features like Intel PT to get real-time, hardware-level visibility into the code being executed. This means we can tell the KAFL agent which runs on the host to focus specifically on the COM server's process in the guest VM. It can then trace the coverage without a problem, even if the process is highly privileged or protected by the operating system. That's why it's such a powerful solution. It bypasses the traditional difficulty of getting code coverage in protected process, making it an ideal choice for hunting common bugs in the Windows corner and user space. Now, for a tricky problem, how do we find the correct virtual address inside the guest VM image? Things get complicated when there are many processes with the same name as our COM server. For instance, svc.host.exe can run dozens of different services, each in its own process. So how do we write our fuzzer harness to handle this? We need a smart way to make sure we are always targeting the right processes, no matter how many are running. The solution lies in identifying a unique characteristic of our target COM server that allows us to distinguish it from all the other similarity name processes. The first step is to enumerate all processes in the guest VM using the create to help search to snapshot function within our harness. Since the harness runs inside the guest VM, it can retrieve the addresses of all processes, including the COM server we are targeting. From there, we can get the base addresses and names all the modules, such as DLS for each process. This allows us to iterate throughout the entire process list, find our target process, and then inspect all the DLS it has loaded. This is the crucial step that provides us with a map of the target memory space. We can find our specific server's DLL and get its base address, which is the starting point for calculating the address of the functions we want to fuzz. Once we have all the modules' names, we just need to compare them to our target COM object module. We can get the DLL name for our target COM object by looking it up in the Windows registry using its unique CLS ID. Then we can program our harness to iterate throughout all the modules in our target process, looking for a matching name. When we find the match, we calculate the exact address of that process and tell our agent where to start collecting coverage data. And just like that, we have successfully mapped the code of our target COM server and can begin fuzzing it to look for vulnerabilities. It's a simple yet powerful approach that bypasses the complexities of traditional coverage method. The second, What the Fuzz, is a user mode fuzzer designed by Windows application, making it ideal for target COM object. Unlike hardware-assisted tools like KAFL, What the Fuzz simplifies the fuzzing process by eliminating the need for a virtual machine or VM setup. This allows researchers to quickly and directly test the running process, streamline bug discovery. What the Fuzz is a snapshot-based fuzzer that captures and enumerates a program's state to achieve code coverage. By emulating the process in a controlled environment, it can accurately track which code has been executed. This allows it to generate new inputs that explore unreached code paths, offering a powerful alternative to hardware-based fuzzing for user mode application. What the Fuzz doesn't need to struggle with finding the target server's address. This is because it can dump the necessary information when the fuzzer's harness reaches the target server. Therefore, What the Fuzz makes it easier to fuzz COM servers, eliminating the complex task of finding the server's address. You can simplify fuzz without the struggle. I studied fuzzing various COM objects, and it didn't take long before and it suddenly crashed. The first bug was discovered in the UPnP host service, specifically within the UPnP host.dll file. This library exposed several COM interfaces, but the one containing the vulnerability was the UPnP description manager interface. This interface is responsible for managing device description on the network and the process incoming data. The specific flow was found in the process description template function of the C description manager class. Interestingly, this function first performs a check to ensure the connection is local before calling the vulnerable remove description function. This local only check significantly limits the attack surface. The remove description function, which cleans the registry and tires for UPnP devices, is part of a vulnerable call chain. It calls HR remove presentation virtual dir, which then calls HR remove reroute. While remove description itself might appear safe, the real vulnerability is a logical flow hidden inside the final function HR remove reroute. This is where an attacker can trigger the bug. The vulnerability exists in the HR remove reroute function, which is a global variable, gpvers, when calling the remove reroute method. Although gpvers can be manipulated to cause an unexpected state change in the program, the function itself lacks a direct write primitive. This means an attacker cannot control what data is written or where it's written, making it difficult to achieve a reliable exploit. Due to the lack of fine-grained control needed to hijack program execution, Microsoft classified this bug as a denial of service rather than a privilege escalation. Moving on to the next vulnerability, I found it in the MCP management COM interface. This interface has 8 interfaces. This interface has 8 different methods, but I decided to edit the get authorization header silent async function. This function calls an internal function named getAuthorizationHeaderInterner. What happens inside the function is a bit tricky and presents a classic race condition scenario. The function takes the value of a shared variable and puts it into a local variable v12. This shared variable is the key to the vulnerability. Then the code calls internal release on that value. This is where things getting interesting. Internal release frees the memory associated with v12. Now let's look at the get authorization header async. Does this sound familiar? It should, because this function also calls get authorization header internal. It's the same internal function we just talked about, and that's exactly what caught my attention. This is a crucial finding for a bug hunter. The fact that 2 different public-facing methods, get authorization header silent async and get authorization header async, both call the same vulnerable internal function, get authorization header internal, is significant. 2 separate functions, get authorization header silent async and get authorization header async, both call the same internal release memory management routine without the proper locking mechanism, leading to a classic race condition in an MTA model. When multiple threads try to access the shared pointer, one thread can free the memory while another is still trying to use it, resulting in a use after free vulnerability that causes a crash and a denial of service. Recognizing this familiar pattern of security researcher then create a proof of concept to validate the extent of the bug and demonstrate the crash. And it's a demo time. First, check the latest Windows version. And start our target process. And check the PID and attach the debugger to target process. And we run the POC code, so wait lately. There will be crash on the target server on running in system privileges, and that it can be lead to privilege escalation settings. Okay. Based on analysis, we can confidently conclude that the bug we found, which is assigned the number 2025-29841, is a significant race condition and use after free vulnerability. This discovery validates our systematic bug hunting methodology, which combines the deep understanding of COM architecture of focus on high privilege targets, and the use of sophisticated fuzzing frameworks to uncover complex vulnerabilities in well-vetted system service. Now let's look at the feature of this research. A key next step is to automate the entire fuzzing process to make it more efficient. This involves writing a script to parse IDL files and automatically generate intelligent mutate inputs based on the method and arguments defined within them. This target approach is more effective than sending random data. Additionally, we can build a feedback loop into the fuzzer so it can automatically switch to a different method if a current one fails to increase code coverage. This dynamic and adaptive strategy maximizes the chance of finding new vulnerabilities without wasting time on dead ends, leading to a full automated and highly effective COMposures. And thank you for your time and attention. It's a pleasure sharing my journey with you. And someone has the Q&A. Yes, thank you.
So before you were speaking about access control and like a system user can perform or a system user may get access POM object.
Yes.
Once you are connected to a POM object standard user, is there more granular, like this user can only call these functions? Or is it like a general like Boolean for an admin or you're not an admin kind of thing?
So can you speak one more time?
Sorry. So when you've got like when you connect to a POM object as a low privilege,
Yes.
is there any situations where you can only call a subset of all functions?
Yes.
Does that answer like? Do you understand?
Sorry.
So can't do that. If you're low privilege
Yes.
and the COM object might have 20 functions.
Yes.
Is there any situations where you can only call some of those but not all?
Yes, not all. That's it?
So can you limit what a user can call?
No, we can call any functions of the list of the components. So that is the researchers want to anything. So that's not limit.
Yes.
Is it all right? Thank you.
Yeah, thank you.
Anyone else? Yes.
When you're saying that you're defining, you mark it on CVSS as a local privilege, like attack vector.
Yes.
Is there any reason why it's coming down remotely?
Like CV 2025, I found it.
Yeah, yeah.
No.
Why would you not be able to access a computer or a VM or whatever and execute it?
Oh, my bug is only attack to in the local, so that can be lead to remote code execution. So, and my target call object has only local process environment, not on the DCOM, so it can be lead to only local privilege escalation. Then Microsoft to lead to adjust the local privilege escalation too. Thank you. Anyone else? Okay, nobody has the Q&A, so thank you for your attention and time. Thanks.